Hello, welcome to this screencast on the optimization of the electric efficiency of the electric steelmaking process. I'm Jesus Hernández. I take part of the Horizon 2020 Marie Curie European Project Pronto. I'm a PhD student at TU Dortmund University and a research engineer at Acciai Speciali Terni in Italy. So the contents of this screencast are as follows. First, I will provide some background. Then I will go through the dynamic optimization that we proposed in our paper. Then I will describe the electric arc furnace model that we utilize in our dynamic optimization framework. I will provide also some numerical and industrial results. And finally, I will wrap up everything with some conclusions. Let us talk now a little bit about the modern steel production scenario. So there are various steel production methods, and among all of these, the electric steel making is the cleanest route of producing crude steel. Because of this fact, during the last decade, the share of steel production via the electric route has increased steadily, from 25% approximately in 2012 to almost 29% in 2018. But what is the steel making via electric arc furnaces? So it is a batch process where metal scrap is molten and partially refined. The main inputs to the process are the electric and the chemical energy in the form of methane and oxygen. It is a discontinuous process because the charging takes place in stages and the process has to be stopped every time that you need to make a new charge. It is highly nonlinear. It never reaches a steady state, and the biggest challenge maybe is that there are no available measures of the most important dynamic state during the process. And this is how it looks like. In the left-hand side, I show a picture of the external shell of a fully operative electric arc furnace. And in the right-hand side, I show a representation of the interior of the furnace itself. So we see the electrodes, which are used to introduce current into the furnace and to create the electric arcs, which are the main source of energy for the process. We also see the oxy-fuel burners that can be used to introduce methane and oxygen, and they create the oxy-fuel flames at high temperature that help or aid to the melting process, and they at the same time can work as an oxygen lance during the last stages of the process. So you just use the same burners only for injecting oxygen, and this helps to increasing the temperature in the liquid bath as well as to the refining of the crude metal itself. There are a few challenges that still need to be addressed in the steelmaking process. On the one hand, you have the economics. Steel production nowadays is a very challenging market, and it's a very challenging industrial area where the overproduction globally has impacted the economics of many plants. And on the other hand, we have the CO2 emissions, which are of big concern in the current times. To address these challenges, then we propose a dynamic optimization framework that enables the integration of demand-side management algorithms with advanced process control strategies, which combine aim at optimizing the economic and environmental performances of the electric steelmaking process. Let us now talk or introduce the dynamic optimization proposed in our paper. From the automation pyramid point of view, a feasible application today with the work that many researchers have carried out during the last decade is as follows. One can think about integrating in a unified optimization framework, scheduling, dynamic optimization, and MPC. Many works have been focused on the scheduling layer, taking into consideration demand-side management, and also many authors have focused into the MPC, trying to optimize the energy inputs for the burners and the oxygen lancing. In this work, we present a different approach that tries to optimize the efficiency of the furnace and tries to fill the gap between these two approaches. In more detail, this is how we envision the unified optimization framework. In the scheduling layer, optimal schedules are computed from a purely economical point of view, considering intraday market conditions as well as the status of the plant. This allows to take advantage of possible economic returns that come from playing into the energy market, as well as decentralizing the energy consumption from the furnace and playing around with other elements in the plant itself. Then the algorithm will compute an optimal schedule with different batches and different lengths of campaigns of different types of steel. This information then will be communicated to the dynamic optimization layer, where the optimizer will compute the optimal voltage and impedance inputs for a single campaign, considering the electrical power limitations as well as the number of batches in a campaign, which are communicated, as I mentioned before, from the scheduling layer, and also taking into consideration possible variations in the raw materials, as these can impact heavily the length of a batch. Finally, in the MPC layer, one can perform two types of computation. On the one hand, from batch to batch, one can compute the optimal input for the oxygen lancing during the refining stage, taking into consideration the terminal measurements of the temperature as well as steel composition. And on the other hand, one can use online measurements to optimize the efficiency of the combustion process into the oxygen fuel burners. Some representative authors are as I show here. In this slide, I introduced the dynamic optimization framework that we presented in the paper, and this aims at minimizing the losses of the batch in terms of the voltage and the impedance set points of the electric arcs, considering the dynamic model of the furnace, the algebraic equations that come from the heat exchange phenomena, the relationship that exists between the power of the arc and the length of the arc itself, the constraints that are communicated from the schedules, as well as the required terminal constraints, as could be the final temperature of the melt or the chemical composition of the metal. We decided to pursue this optimization in terms of minimizing the losses, because minimizing losses is equivalent to maximize the energy efficiency of the process. In addition, by maximizing the energy efficiency, one can obtain two benefits. On the one hand, the cost of operation are reduced, which is very important for improving the economics of the plant. And on the other hand, one aims also at improving the economical footprint of the process, which is very relevant. Also, with this approach, we can avoid a greedy behavior of the algorithm that aims only at maximizing profits, regardless of how efficient the process is. So in this case, with this objective function, the economic benefits comes from the following consideration. In the bottom part of the slide, I present the variable cost of a batch, which are as follows. The cost of the electrodes is approximately 35%. The cost of the electricity is almost 60%, and the cost of the energy fluxes is about 5%. When the losses are minimized or the efficiency is maximized, certainly the energy consumption will be reduced. Therefore, this part of the variable cost will be reduced. And also, by minimizing the losses, the energy that arrives to the electrode is reduced. Therefore, the electrode consumption is reduced. And from this point of view, also this component of the variable cost will be also reduced. And this is how, with one single objective function, we can tackle both environmental impact and improving the economics of the plant. Let us now introduce the electric arc furnace process model. So we envision the electric arc furnace as follows. It's a white box with different types of energy inputs: the electric arc, the oxy-fuel burner, the charged coal, oxidation of solid metal, and oxidation of liquid metal. Each of these energy inputs is subject to an efficiency parameter, an energy efficiency parameter that is computed from first principles and which will establish how much of the total energy from the source is actually transmitted to the process, which will contribute to the main phenomena that takes place during most of the batch, which is the melting of the solid metal and the heating up of the liquid metal. Important considerations that we had during the development of the model are as follows. The impact of the electric set points on the geometry of the electric arc. This is particularly relevant if one considers the radiative heat exchange from the arc to the rest of the phases in the furnace. Therefore, we consider how the operative power level affects the length of the arc. We also consider that the heat exchange between the arc and the rest of the phases occurs via radiation mechanisms only. And for these computations, we utilized DC circuit analogy for computing these heat exchanges, and also utilized Monte Carlo algorithms to compute the view factors that are required within the DC circuit analogy. An improved geometry of the solid scrap in the furnace was considered. Most of the existing electric arc furnace models assume that the solid metal assumes this cone-frostrum geometry during most of the batch. Unfortunately, during our observations of the process in the furnace in Acciaierie Speciali Terni, we noticed that this geometry cannot describe properly the process, especially during the early stages of the batch. Therefore, we took considerable amount of time observing the process and proposed to model the solid phase of the furnace instead like as a hollowed cylinder geometry. And finally, we consider the mechanisms that restrict the energy contribution of the oxidation reactions to the process. One of these, for example, is the oxidation formula or the corrosion formula, which is presented here. Let us now introduce the numerical and industrial results. In this slide, in the left-hand side, I present the simulation of a batch using standard operative conditions for a batch. In general, these standard operations are as follows. So a batch is operated during the whole batch at a constant power level, which is presented by this constant line, and the length of the arc is reduced as the batch progresses in time. This strategy aims at reducing the energy losses that occur through the walls. So the length of the arc is reduced. And we have, in the bottom part of this figure, we have the energy that arrives to the solid metal from the arc. We have also the energy that arrives to the walls. The diamonds represent the energy that arrive to the electrodes. The crosses represent the energy that goes to the lateral part of the electrodes. And finally, the dotted points that are actually hidden behind the triangles represent the energy that arrives to the roof directly from the arc itself. It's important to consider or to remark that this is related exclusively to the electric input, therefore to the radiative energy from the arc. On the right-hand side, I present the optimal melting profile computed by the algorithm and is as follows. So the algorithm suggests that optimal efficient operations are achieved by operating the early stages of the batch, it means immediately after every charge, at high power levels, and reducing the operative power level as time progresses in time. And this makes sense because what the algorithm is trying to do is to reduce the energy losses as the metal melts, because as metal melts, a larger area of the walls and the roof is uncovered. So the algorithm tries to reduce these losses. And a very interesting divergence from the standard operative practices is that the algorithm also aims at keeping the arc length as long as possible. So while in the standard operations, the arc length is reduced, in the optimal operations, the arc length is maintained as long as possible. In the bottom part of this figure, we see that if we compare with the standard operations, towards the end of the batch, there is a minor reduction of the energy that arrives to both the electrode horizontal and the roof of the furnace. This implies that especially towards the end of the batch, the energy that arrives to the electrode is reduced, therefore the electrode consumption is also reduced. Let us now introduce our study case. The optimization algorithm was used to compute the optimal voltage and impedance set points for the process, and we took into consideration two different grades of stainless steel. This optimal profile then was implemented in one of the ultra-high power electric arc furnaces in Acciaierie Speciali Terni, and 19 production batches were run. These test batches are real batches, and the product of these batches in this moment should be in one of the clients of Terni worldwide. So the results are as follow. In this slide, we present the results of in terms of the batch time and the energy demand improvements for the two considered types of steel. In the left-hand side, for steel grade A, the gray light column represents the average of the test batches, and the dark column represents the average of 1 year of production. This is data of 1 year of production. So in comparison with the standard average, we see that we managed to reduce the energy consumption of the batch by approximately 4.6%, and the batch time was also reduced by approximately 4.3%. For steel type B or steel grade B, the energy demand was reduced by approximately 1.7%, and we observed no improvements in terms of the batch time. Okay, now let us wrap up this presentation with some conclusions. So we believe that today, with the work that many researchers have done, it's possible to integrate scheduling, dynamic optimization, and MPC into a single optimization framework that aim at improving the economics of the plant, taking into consideration demand-side management and efficient process operations. Scheduling algorithms, however, must consider the correlation between the operative power level and the batch time, because operating at different power level produces different batch times, and this relationship can be computed using the proposed model in this work as well. A dynamic optimization framework that improves the energy performance of the steel production process was presented and validated both numerically and industrially with real operative batches. The algorithm computed a mode of operation that reduces the energy demand of the process. Optimal operations were achieved by operating at high power levels immediately after one charge of the furnace was done, and by reducing progressively the power level as the batch progresses. The effectiveness of the optimization here proposed was validated in a fully electric arc furnace, and energy savings of 4.6% and 1.7% for two different grades of steel were achieved. We thank you very much for your attention, and we gratefully acknowledge the economic support of the Marie Curie Horizon 2020 European Industrial Doctorate Project Pronto.